Welcome back to BitLearn. Before we dive in, let's take a quick minute to zoom out and look at what we have done so far in this series. So far in the modern OS design series, we have built the foundations step by step. We started looking at how operating systems evolved, how they are structured. We looked at processes, threads, how does the OS create this illusion of parallelism, speed. We looked at CPU scheduling. How does the processor allocate CPU to different processes? We looked at memory management, virtual memory, paging, so many things. So here is the next natural question. If every process lives in its own isolated memory space, how do they ever talk to each other? That's what today's episode is all about. If you're new here, I would strongly recommend checking out the earlier episodes. This kind of builds in the right order. If you're finding this series useful, do consider subscribing. It really helps this small channel grow and reach more serious listeners and learners. I'm also currently working on a full book on modern operating system design that expands this entire series into a more structured academic format. You will find the details in the description below. So with that context set, let's move on. So in today's episode, we're going to look at inter-process communication, or IPC. So think about how a modern operating system is designed, not in terms of features or performance, but in terms of trust and security. Every process runs as if it is alone. So my browser is running here, it's alone, it's not allowed to talk to anybody else unless the designers allowed it to. It has its own memory, it has its own address space, its own little universe. And that design is not accidental. That isolation is what keeps the system stable. So when a buggy program crashes, it doesn't bring down all the other applications along with it. So that's how it is designed. Now kind of pause for a moment and ask yourself this very simple question. If every process is so nicely isolated, how does anything actually get done? So for example, I have a timer running. If it times out, it's going to pop up a window. But I also have my browser, my video editor, webcam, everything running. How does this pop-up window comes on top of all these applications? How does it stop the other application? There is some kind of communication going on, right? So this is where IPC comes in. It's called inter-process communication. This is how two processes communicate with each other. IPC exists because direct access to somebody else is forbidden. Think of it like your home. You have your home, you are the process. You have another home, you have a neighbor, that's his process. So both of these processes by design, they are not really meant to communicate with each other unless the owners intend to do so. So IPC exists because direct access is forbidden. It's not just discouraged. You don't want your neighbor to be peeking into your window unless you want him to. Same thing, your neighbor doesn't want you to be walking through his door unless you allow him to. So processes are not allowed to peek into each other's memory, and that is something good for security. So IPC is not about breaking this isolation. Just because we have IPC doesn't mean suddenly I can just jump in through my neighbor's window and get something done. So think of it like this. IPC is not about sharing data freely, but it is about sharing responsibility and safely. So now let's look at it. If you step back a little, you will notice that there are two significant or most important ideas in inter-process communication. Almost all of them, they fall into two broad ideas or categories. These two are the crux of every IPC communication. One of them is shared memory. The other one is message passing. So to put it very simply, we talked about this example of two homes and neighbors. Shared memory is something like a shared backyard. If I want to send something to my neighbor, I dump it in my backyard, he'll pick it up. Or if he wants to send me something, he'll dump it in his backyard or the shared backyard, and I'll go and pick it up. Remember, that backyard is shared. So if I mess it up and make it dirty, even the other process, my neighbor also has a messy backyard. So if he messes it up, I have a messy backyard because we share the same one. The other one is message passing. It's more about writing address, details, everything in an envelope and passing it, and it will somehow get delivered to the neighbor. So let's look at the implementation or details of how these work. To begin with, let's start with shared memory. So in shared memory, the operating system creates a region of memory and maps it into multiple processes, something like the shared backyard we talked about. Once that is done, communication becomes incredibly fast because the same memory space is mapped into both of the processes. There are no kernel calls. I have the same address space available in my process. Same thing is also available in my neighbor's process. So no copying, just read and write. I put a variable, I update a value there. It's read directly by my the person who wants to read it. So it's something like a driver. So a driver looks at, let's say, this particular webcam. It reads a series of bytes, the image, and puts it in a shared area that is picked up directly by the driver because they both share the same shared memory. It's just a wild example I'm giving you, but basically I'm telling you that there are no kernel calls, no context switching. It's just there. So when the CPU schedules my webcam's driver process, he gets a chance to just read from the shared memory. When the CPU schedules the actual the hardware process or the layer that reads from the hardware webcam, he will just write everything into a shared memory. When the video editor is scheduled, he can read from the same shared memory. So you kind of see a seamless process. Everything appears very fast, but it comes with a cost. Everything has to be very disciplined. One person messes up and the backyard becomes a dump yard. So here is the most uncomfortable question. Who makes sure that two processes don't write to the same memory at the same time? The answer is nobody. So if the driver is writing something to the shared memory, it is up to the applications to coordinate among themselves. If I write to the same area, I might overwrite what he's writing. So the operating system sets up memory and then steps away. It does not enforce ordering. It does not prevent any race condition. So it does not guarantee correctness. It's up to the application. So that is why shared memory is both the fastest and most dangerous form of IPC. Unless all the three applications are good friends and they're all designed properly and they all agree on how they want to read memory, a single mistake can corrupt the entire shared state and crash multiple processes. All three of them could fail. So I talked about this backyard example. It could become a complete dump yard in a flash. So shared memory only works when it is paired with careful synchronization. So I can't just rely on the three developers having good relationships between their design ideas, right? So there is a mechanism to ensure that they can work together. Because I am writing a device driver, I don't know who is writing this video editor in some other place in the world. He's writing the video editor. He also needs access to the shared memory. So this is where synchronization comes in. Synchronization is done through locks, semaphores, and a lot of discipline. We'll come back to that in a later episode, but we'll only talk about the IPC mechanisms without the synchronization mechanisms in this episode. So do follow up on the other one if you really like this topic. Make sure you look into semaphores, locks, and the other disciplines, mutex. Without the locks and synchronization mechanism, this whole episode will be of no use. So this is more like part 1 of IPC. The next one is going to talk about the synchronization mechanisms. So now, okay, let's continue. Let's look at message passing. So in message passing, the processes do not share memory directly. I gave you this example of an envelope. If I'm passing a message to my neighbor, I put in his address. The post department, the postman picks it up. He will route it to the right recipient or my neighbor. So they exchange messages through managed channels. So these are kernel managed. We'll talk about that. The operating system validates the message, makes sure it is well constructed. It buffers it if necessary. Then it safely delivers it to the receiver. So I write an envelope and say, hey, come over for dinner in the evening. I put it in an envelope and I post it. It goes into the postal system. The postman will somehow come and deliver it to my neighbor. He opens it. So this post job is actually done by the operating system. So it delivers it safely to the receiver, it validates the message, and it will also buffer it if necessary. So buffer is something like everybody on the street is writing messages to each other. So the post office is going to collect all these envelopes, put it somewhere, make sure it is delivered the next day morning or in the next cycle. So that is the buffering part, where you collect all these messages, hold it for a while if necessary, and then deliver it to the receiver. So this is much slower than shared memory, but it is much easier to think through that. So it leads to an important design question. Do you need raw speed or do you need some clarity and safety? Operating systems constantly have to make that trade-off. So the simplest message-based IPC mechanism is a pipe. So a pipe is like a queue. You write something into the pipe, it's available on the other side. A pipe connects two processes. So me and my neighbor, we can set up a pipe. And I just keep dumping every information that the neighbor needs to read into the pipe. The other person reads it. Data flows in the same order, like water flowing through a hose. So there's something more elegant about pipes. They're not clever. They don't carry any structure. They just move the bytes around. They're clever because they make sure that the whole mechanism is pretty simple. I write on the writing end and somebody else reads on the reading end. That's it. They are not yet bidirectional unless you create a bidirectional pipe. And yet they power some of the most powerful patterns in most Unix systems. The output of one program becomes the input of another. So if you remember your shell commands, you can do a ls, a list of a directory, and pipe it to, let's say, more. More is another utility which is going to take the entire list of directories and page it. So these are two different utilities, but you're piping the output of one command into another. It looks seamless, right? You do ls pipe more and you see a nicely paged list of all directories, folders in your disk drive. What's happening is a pipe has been set up between these two commands. The output of one is piped to the other. It need not be output, it can be more dynamic, but that was an example. So now let's consider this. What if two unrelated processes need to communicate? I was talking about somebody writing a video editor and somebody writing the webcam's device driver. So that's where things like a FIFO can be useful. They kind of live in the file system. They allow independent processes to connect without knowing about each other. So how this works is, if you take the previous example of a anonymous pipe, when I create my process, I create the pipe as well, and that is basically connected to the other one, the other process. So there is no naming, there is no identity. It's just a shared pipe. Now, if both these processes, they don't live at the same time, maybe there is no overlap. What I mean by that is the webcam or the driver for the webcam is capturing images. It's going to write it to the file system. The video editor, whenever it comes up, it's not going to be a huge gap, but let us say a fraction of a second or a few seconds out of sync. It comes up, it needs the image data now. What does it do? It can use a named pipe. It opens up the FIFO named pipe and can start reading from that, assuming that this is a dynamic pipe where the webcam is writing image data. So this kind of allows for independent processes to connect without knowing each other, and they need not be synchronized as well. So as the systems go more complex, a raw byte stream is not going to be enough. So we may need a much more structured way of communicating. That's where message queues come in. So message queues allows processes to exchange discrete messages. It's a fully properly formatted message with a proper header, everything. And the message body may be very specific to the application, but the message format or the envelope itself is pretty clear. So if you go back to the old postal system, so the envelope concept is pretty clear. There is an envelope. There is something that you fold, you kind of glue it together, you write the address. All of that is always the same for anybody who's sending a message. What is not open to the public is the actual body of the message. So message queues allows us to define such a structure. They are ideal for asynchronous system where I send out a message. I don't know when it is going to be read, but I'm pretty sure it will be delivered. So we have things like event handlers, logging pipelines, we have background worker threads. All of them work like that. So they kind of sacrifice a bit of performance in exchange for structure and reliability. And in real time, that trade-off is often worth it, because I can't ensure that these two processes are up and running at the same time. I write a message and it will get picked up immediately. I can't really ensure that. So that is where this particular design is pretty useful, where we use message queues. Now let's revisit shared memory one more time, but with some more clarity this time. So shared memory gives you a lot of speed, but it gives you almost no safety. The operating system allocates the memory, enforces some permissions, and that's it. So ask yourself this: if two processes share a memory and there are no rules about who writes when, is that communication, or is it just going to be a lot of chaos? So without synchronization, shared memory is not IPC. It is just uncontrolled access to shared state. It becomes IPC when you start enforcing some synchronization with mechanisms like mutexes, semaphore, all sorts of locks. So this is why shared memory is almost always paired with a synchronization mechanism. Whereas for a message queue or a FIFO, a named pipe, the synchronization mechanisms are not that explicitly captured, but it's there in the design. And this is why IPC and synchronization are inseparable topics in operating system design. So let's look at how a major leap in IPC design comes with sockets. A socket is a little more extended. A socket kind of unifies the local and remote communications under a single abstraction. So when we talked about shared memory, we talked about two processes on the same machine sharing a backyard, sharing a shared memory where they can dump information and each of them can pick it up. What if this other process is actually on a different machine? So that's where sockets come in. Sockets unify the idea of IPC and remote communication into a single abstraction. So from the application's perspective, talking to a process on the same machine and talking to a process across the network, they feel more or less similar because all you're doing is opening a socket. You get a name, you use that socket, write your bytes, get it out. So Unix domain sockets handle the fast local IPC. Network sockets extend the same model across different machines. So this is by design. It is a choice that allows systems to scale naturally from local programs to distributed architectures. So that's how powerful IPC is. Once you understand the fundamentals of IPC, you're not very far from a distributed system. You're very close. So let's look at signals. So this is even more interesting. Signals are like not conversations that we do. They're more like interruptions. So signal is like telling a process that something has happened. Maybe it should stop. Maybe it should handle an exceptional condition. So signals carry very little information because they need to be sent very quickly, and they offer very few guarantees. It's not guaranteed that you will always receive your SIGINT or SIG, whatever signal you are sending. They are useful for control, but they are terrible for structured communication. So don't expect to send your complete communication message as a signal. So it's more for interrupting the process to say that, hey, there is something more important that's happening in the system. Somebody has pressed the shutdown button. Just roll up quickly and wrap up your work, and I'm going to shut down the machine. So that is a typical signal. Or a signal could be more like, hey, there is something coming on a pipe. Do you want to read that? So signals are more like a very quick flag or an interruption to the process saying, okay, you're doing your job, I know, but here is an interrupt. There is something that happened in the system. Do you want to address that? So that is basically what a signal does. So finally, let's look at the bigger picture. The choice of IPC mechanism shapes the entire operating system. So in a monolithic kernel, they rely less on IPC because everything is right there in the same process space or the memory space. And many components kind of live in the same address space also. But in a microkernel, they have to rely on IPC everywhere because your OS is now designed as a small set of cooperating services. They need to talk to each other. Hybrid systems, they kind of balance this isolation and performance based on how they want to decide it. So OSs don't pick one IPC mechanism. They actually offer all of them. They combine all of these variations to give you the best performance and also best isolation. So it is kind of always a trade-off. Like I keep telling you throughout this series, OS design is kind of a trade-off. It teaches you a lot about life as well. So the OS is acting as a broker of trust. It decides how isolated components can be and how we can make them communicate without destroying system integrity. So good operating system design lies in knowing where to draw these lines. So in the next episode, we will build directly on these ideas and we'll start talking about synchronization, because a lot of people could be using these IPC mechanisms, but we also need to make sure that they are in sync and they don't interfere with each other. So what happens when multiple things happen at the same time? So let's look at all of those details in the next episode. So meanwhile, if you're enjoying this series, do subscribe, hit the like button, and also look at the previous episodes. If you think this is a bit too much, what you have to do is go back, look at the previous episodes, and how do we tie it all together to design a good operating system. Of course, just a reminder, this is all going to become a book very soon. Do check the description. You will find a link to the book, and it will help me a lot if you want to purchase the book and if you like it. Meanwhile, do drop some comments and keep learning. I'll see you in the next episode. Thank you for watching.